Hey guys, lesson 6, kinetic molecular theory. I apologize for the length of the last lesson, but I had to do some math with you, so it takes a little bit longer. For this lesson, you will state and understand the KMT, kinetic molecular theory. Okay, so a more detailed look at the different phases of matter. We've discussed solids and liquids at depth, so now we need to talk about gases because they have specific behaviors, and when certain variables change, then gases are going to behave differently. So we need to talk about that. The KMT is a model that's used to explain the behavior of gases in terms of the motion of their particles. So the major assumptions of the KMT include that the volume of the gas particle is so small that it is negligible in comparison to the volume of the container in which it is confined. Okay, so if you think about it, very, very tiny compared to the volume of the container. Gas particles do not attract each other, so there are no IMFs. So this is the assumption that they don't attract each other in any way whatsoever. Gas particles move in random continuous motion, and they don't stop, which is an assumption. The gas particles are perfectly elastic, and they lose no speed after they collide with one another or with the walls of the container. Okay, the KMT is based on the concept or model of an ideal gas. So what is an ideal gas? We need to look at that. And an ideal gas is something that is theoretical, and it's used to predict the behavior of real gases, such as oxygen or hydrogen or helium. Remember, diatomic elements, those are gases. Okay, so remember, gases are kind of like all over the place, and I'm doing this to show movement. But when they do bump into walls and things like that they're confined in, they bounce off those walls and go back at the same speed, okay? The assumptions above are not true of real gases. So these are major assumptions of ideal gases, but not real gases. And the gas laws are not 100% accurate when we talk about the real gases for this reason. So we just say ideal gas. Okay, so there are problems for the KMT. Now remember we said that the assumption is that their size is so small that it's negligible. So the problem is if we have something that has large molecules or atoms, that's going to present a problem. Okay, because big particles have high intermolecular forces. Also, we talk about their speed. Okay, and slow motions actually, or slow movements, are subject to more IMFs. So that's going to be another problem for us, molecules that are slow moving. Okay, another problem for the KMT that doesn't follow the assumption is small volume containers. Because those small volume containers mean that there are going to be more collisions of the particles. Okay, because they're confined and squished down together, so they're going to bump into each other. Think about a crowded room. Okay, real gases follow the KMT best under these conditions, and these are very important. You have to know this. Okay, when something is nonpolar, they have low intermolecular forces. Okay, and that's very important. You don't want them to be stuck to each other. They want to be able to spread out. They don't want to be so confined. Okay, for gases, ideally. All right, high volume means that there's low pressure, right? You have a big container full of a gas, not a lot of pressure. They have a lot of space to move around. Think of the molecules being able to spread out more. Fast moving generally will mean that there's high temperature. Okay, when you increase the temp, everything moves a lot faster. You get hot and it starts to speed up. Okay, and then finally, small size. This is what we need for a gas to follow the KMT. All right, so let's look at the collision theory. Again, something else that you have to know. In order for a reaction to occur, particles have to collide, hence collision theory, with the proper amount of energy and with the proper angle and position. All of these things have to exist. You need energy, angle, and position for a reaction to occur between gases. All right, so let's look at our gas laws, and gases follow these laws and give us clue as to their behaviors. The first one is Avogadro's law. Gases are at the same temperature, pressure, and volume and have the same number of molecules or particles. All right, so again, remember Avogadro gave us the number of molecules, 6.02 times 10 to the 23rd. So this is where Avogadro's law comes from. Same number of molecules as long as every gas has the same pressure, volume, temperature. Pressure, volume, and temperature. Okay? pressure, volume, temp. They're all equal, so therefore they have the same number of molecules or particles. So which one has more gas particles? Well, I just said it, okay? They all are equal. So it's not a trick. They're equal. Okay, and that's because same pressure, volume, and temperature follows Avogadro's law. All right, number 2 says which one will behave the most ideally. Now going back, we want to look at the ones that follow all of our rules. And they have to be small, okay, think about that. Low IMFs or nonpolar. Well, if something is by itself, it's going to be nonpolar or inert. We want to find something that might be less reactive. So in this case, the argon is going to be the one that behaves most ideally because, one, it is a noble gas, inert, okay, and no IMF, all right? So it doesn't have any intermolecular forces. Argon molecules will not attract each other, basically. And which one has the most atoms? Well, let's explain this, and this is easy. We're just going to look at the subscripts, CO2, and how many elements are in each. So CO2, right, has 2 oxygens and 1 carbon, so this has 3 atoms. Hydrogen, okay, has 2 atoms of hydrogen, and then argon is by itself and only has 1. So the answer is carbon dioxide for that reason. All right, moving on. So the combined gas law, we talk about Avogadro's, now we talk about the combined gas law. We use this for gases only, okay? So if you see solid or liquid, we cannot use this formula when all 3 variables are changing. Nothing remains constant in this type of problem. So reference table T gives us the combined gas law, and as long as we are given pressure, volume, and temperature, we can use this formula, and we'll look at some practice problems. Note, you must use Kelvin, not degrees Celsius for calculation to do the for the calculation to work. Okay, so if you don't convert, remember, from Kelvin to from Celsius to Kelvin, then you can't do the problem. So remember, it's going to be degrees Celsius plus 273 to give you Kelvin. All right, so here let's look at a sample problem. Gas has a volume of 100 milliliters at a temperature of 20 K and a pressure of 760 millimeter of mercury. What will be the new volume if the temperature is changed to 40 Kelvin and the pressure to 380 millimeters of mercury? Now here's a new piece of information. 760 millimeters of mercury is equal to 1 atmosphere. So basically what we're saying is this is at standard pressure right here. Okay, now we're going to use our P1 V1 over T1 equals P2 V2 over T2. Okay, remember initial and final, that's what the 1 and the 2 mean. So we see V1 is 100 milliliters. Next is our temperature, T1 at 20 Kelvin. Pressure, 760. Now, as long as your units are all the same, okay, and temperature is in Kelvin, then it doesn't matter. Okay, it doesn't have to be in ATMs or kilopascals as long as it remains constant throughout the equation. Okay, and then the next set of information they give us is the final, okay, the final volume and temperature. So or the final temperature and pressure, and they want to know what the new volume is. So that's going to be V2. And we're going to put a question mark because that's what we're solving for. Temperature 2 is 40, and our pressure 2 is 380 millimeters of mercury. Kelvin, put all the units in there, millimeters of mercury. Okay, let's set up our problem according to our equation. Right, so we have 100 times 760, and I'm going to leave out the units here so that you can do the calculation, and divide by 20. Remember, sig figs, okay, for this one will be important, and then we are going to put in our 380 times V2, that's what we're solving for, over 380. Okay, do your calculations, divide this by 20, multiply by 380, and then again divide the whole thing by 380 to get your V2. Okay, our new volume will be 400 milliliters. All right, let's look at the next sample problem. An ideally behaving gas occupies 500 milliliters at STP. So our initial volume and our initial pressure Okay, our initial temperature and pressure will be based on standard temperature and pressure. Okay, now we look at our final pressure here is in kilopascals, so we need to use the standard pressure in kilopascals, which is 101.3. So pressure 1 is going to be 101.3 kilopascals because we're keeping our units constant. Okay, our temperature is going to be 273 Kelvin because that's based on table A in your reference table. Okay, and then it tells us the volume, 500 milliliters. Now it wants to know what volume does it take up after. So that's V2 again we're solving for. Temperature, 546 Kelvin, and our pressure is 980 kilopascals. Okay, again, if I'm going too fast, remember you could pause this, fill out your notes, and then go back and listen to me. All right, so our 101.3 kilopascals times our volume, which is 500, all over our initial temperature, 273 Kelvin, equals, okay, V2 we're solving for. We're going to put in our 980 kilopascals all over our temperature, 546 Kelvin. Now notice, this is actually double. So we doubled our temperature, okay, and we changed our pressure as well. So now we're going to solve for V2, plug that in to your calculator, and you will get 103 milliliters. Now, just to see if it makes sense, we started with 500 milliliters, and we increased the pressure, so it means you're kind of condensing it, okay? And then the volume obviously has to get smaller because you're squishing it down, okay? And you have greater temperature as well, so molecules are going to be speeding up as well. So both Avogadro's law and the KMT can be used to explain the relationship between pressure, temperature, and volume of a gas. All right, so here's an easy way to remember the relationship, and it's really fun actually. At the top of your next page, you'll see a large P, T, and V, and they have to be written from left to right in alphabetical order for this to work. So what you're going to do is you're going to place your finger on whatever variable remains constant, okay, and then you're going to move the paper for whichever one you want to decrease or increase. So let's look at this for an example. If pressure decreases at a constant temperature, so put your finger on the T, okay, and we're going to decrease pressure. So we're going to move your pressure down, okay? Keep your finger on the T, bring your P down, and now volume is actually going to increase. That follows rule A, okay? B says if temperature increases at a constant pressure, so you keep your index finger on P, and we're going to increase temperature, so move your T up, and then your V is going to also go up as well. Volume increases. Okay, so that checks. Now your last example, if temperature increases, okay, we're heating the gas up, and we keep the volume constant. All right, so we keep our finger here, we move this up, then our pressure is also going to increase as well because you have faster moving particles in the same amount of space. So now your pressure has got to increase a little bit too. So does this all sound logical? Yes, have fun with that, okay? Finally, what I'd like you to do is use the practice problems that I did in the lesson and do some practice on page 15 of your homework packets. And you will have a quiz in the near future. I will probably give you a heads up about a day or so before. Okay?